recording this section. And first of all, as I promised, we will briefly go into repetition of steps related to regression diagnostics, but currently in SPSS environment. So I will show you at least how we can detect outliers or influentials. So it means some extreme points in your data matrix for linear regression. Then I will show you also how we can perform Glejser's test for detection of heteroskedasticity. And last step, but this will be very, very similar to GEMOVI environment, will be to show tools for detection of multicollinearity. So first of all, we will try to cover detection of points that can influence your results. It means mostly your individual slopes for individual predictors can be biased upward or downward, it depends, and we know that this is not very nice for our results, that one point could influence results, so that's why we would like to find these cases in our data and maybe exclude these cases from the computation. We know from previous discussion and from previous analysis that we have one extreme case in our data. It is the case 155. So here it is. So it is extremely big flat. Its size is nearly 450 square meters, but the price was quite low one in comparison with its size. It was slightly below 3 million Czech crowns. So we know that this is really influential point, and we detected this point not only by regression diagnostics, but also by dot chart, but still we would like to show capabilities of SPSS in detection of these outliers. So if I would like to detect influentials in SPSS, so I would need to visit Analyze, Regression, and Dialog for linear regression, which should be the second one also on your computers. So I can click into linear. So I can, for simplicity, take only prices dependent, and as we didn't include it centered size, so we would enter only size into our data for this brief introduction of regression diagnostics. So price versus size, and if you like to find influentials in SPSS environment, you need to visit option which is save. So the third one here on the right side. So here we are, and you can see that this dialog for saving in SPSS is much bigger than in GEMOVI. I would like also to inform you that in JESP there is no option for saving anything in data. This is a total difference between JESP and GEMOVI. GEMOVI is able to add something into your data matrix. In JESP there is no such option currently still. Maybe there is some development behind. So for us, we need this section, which is panel on the right side in the middle, which is called simply, and I guess this is quite good advice from the name itself. So it is called influence statistics. So in this section, you can compute some statistics which we covered theoretically last time. At least here we have DFBetas and standardized version of these DFBetas. Once again, DFBeta stands for the difference of slope if I include and exclude a case from the computation. And if this DFBeta or standardized DFBeta is big one, it means this point is influential. I would like only to repeat that there are some recommendations for cutoffs for these standardized DFBetas, and classical recommendation says that if standardized DFBeta is above 2 divided by square root of sample size, or small n, we use a symbol, then there is influential in your data for which the standardized DFBeta exceeds this limit. So that's standardized DFBetas. And also similar concept is based on DFFits. So this is the difference between real value of dependent variable, so it means price of the flat, and between the estimation of price of the flat based on regression equation. So that's rough or unstandardized DFFit. And once again, for possibility to evaluate statistically these values, it is much better to use standardized DFFits. And once again, recap from previous lecture, recommended level or cutoff is 2 divided square root sample size divided number of parameters. For simplicity, we will be using only standardized DFBetas for the first insight, and for DFFits, it will be nearly the same step. So for simplicity, I will ask for standardized DFBetas. It means that in data matrix, there will be at least 2 more new columns. The first one will be for intercept and its change, and the second one will be for slope. So DFBeta or standardized DFBeta is computed for every parameter that you can find in regression output results in table, which is called coefficients. So it means if I have only one predictor, I will find 2 columns with DFBetas. If I go back into my data matrix, it consists of 263 cases. So it means individual flats. So it means that I will get 2 times 263 values. And I need somehow to find some big values that will exceed the limit. Once again, 2 divided square root of n is recommendation, and to find influentials. So it's quite time consuming and maybe boring process to find influentials by standardized DFBetas. But believe me, this is maybe one of the most sensitive tools for detection of influentials. So that's about these standardized DFBetas. Once again, similar approach could be applied to DFFits. And from GEMOVI, and also just apply the same strategy. We know that another tool for detection of influentials is Cook's distance. So you can find it here in distances, part of the dialog for saving. So if you like also to save Cook's distance in your data, so you can do it here by distances and Cook's distance. So here it is. So that's detection of influentials in SPSS. Once again, capabilities of SPSS are much better and broader than for GEMOVI or CHESP. So here we are, continuing okay. And I guess that we can find some new columns in my data matrix. So here it is. The first one is Cook's distance. It is technically called a COO underlined 1. And you can see that label is very simple, Cook's distance. And there are 2 more columns which are standardized beta for intercept. It is fully described, standardized DFBeta for intercept. And the next one is standardized DFBeta for predictor size. So for us, the most important thing is this second standardized DFBeta, which is called SDB1 underline 1. And now, how we can use these values. So Cook distance, I guess that maybe you can help me and remind me what is recommended cutoff for influentials. For Cook distance, do you remember? What was the value?
It must be lower than 1.
Lower than 1, then there is no influential, and if it is above 1, so it is influential. So first of all, if I would be very, I would say basic user of SPSS, I would go through all these values, and I would try to find whether some value could be above 1. And we can find, and here it is very simple in this data matrix, that case number 155, no big surprise for us, can have Cook's distance as 28. So it is very big influential point. So it means it influences our results a lot. So once again, recommendation would be very simple. Try to omit this case from the computation, as results, at least slope, will be biased a lot. So that's very simple recommendation. And for the same point, we can also find these standardized DFBetas. This is once again 7.11 for the intercept and minus 8.15 for slope. So it means for the impact of size on price. This is for us the most important result here. So once again, the evaluation would be, first of all, try to compute cutoff. So 2 divided square root of sample size. So for simplicity, I will ask Microsoft Excel environment for computation of this cutoff. If you have a calculator, you can use, of course, another tool. If you are able to find square root from 263, you can do it in your head simply. So here we are in Microsoft Excel environment. So I will type 2 divided by square root. Sorry for Czech Excel currently. And sample size is 263. And according to my computation, the cutoff level for standardized DFBeta would be approximately 0.12. So if standardized DFBeta would be above 0.12, it is possibly influential point. And once again, here for case 155, we have standardized DFBeta minus 8.15. It is much bigger. Please compare it in absolute values, so minus or plus doesn't matter. So it is much bigger than 0.12. So once again, recommendation, oh, this is very, very influential point. Please try to avoid this point into your analysis. So that's the same recommendation. And also you can see that it influences not only the slope, but also the intercept quite a lot. 7.11 is once again much bigger than 0.12. So that's detection of influentials in SPSS environment automatically. SPSS also at this output, if you ask for Cook's distance, so you can for simplicity see that for Cook's distance, the biggest value is 28. You know, this is the point number 155. Here is the mean, here is the standard deviation and number of cases from which this is computed. And this table is much broader automatically, as it includes also all other possibilities that can be saved in your data. So it means here we have some predicted value residuals, etc., etc. So that's the first insight, how we can detect influentials in SPSS environment. So once again, very simple recommendation here. Please try to take this case 155 outside from your analysis. And we know we can perform such operation in SPSS by filtering or by definition of missing values. So these are 2 options. So here we are. And this is the first step. So it means how we can detect influentials. And the next step, if I remember well, steps from previous lecture will be to show how we can detect heteroskedasticity. So it means whether the variance of dependent variable or residuals, in other words, is somehow related to the level of some predictors. For simplicity, we will once again take very simple case. So it means price versus size will be once again our analytical task. And we will try to perform Glejser's test in a SPSS environment. This is very, very simple analogy to previously discussion in Chemovi. So if I would go once again into regression dialog, so analyze regression and linear, I will once again go into save. First of all, please cancel standardized DFBetas and Cook's distance, as we would have duplicity of previous columns. And if you would like to save residuals. So you can see a lot of options here in SPSS environment. In Jamovi, if you remember, there was only option for unstandardized residuals. For us, it is enough for Glejser's test, but here we have also standardized student-designed deleted and student-designed deleted residuals. So we discussed theoretically about these residuals and their meaning last time, so we will not recap these. But once again, for Glejser's test, we need to take absolute values of unstandardized residuals. Once again, residual mean difference between real value of dependent variable, so it means real price of the flat, and between predicted value by my regression model. So that's unstandardized residual, only the difference between these two. Jamovi can do it also. I would like only to recap that in chess, there is no such option. As in chess, there is no option to save anything, so we would need to compute residuals as the new variable by regression equation. That's also a possibility. If you like to know how to perform these procedures, please see lectures from last year. So here we are, unstandardized residuals. So here it is, click and continue. If I go once again back into my data matrix, here we have the values of unstandardized residuals. Once again, this is, I would say, mistakes in my prediction for individual flats. So sometimes I'm below, sometimes I'm above real value. And if I would like to compute Glejser's test, once again, you can go back into the last presentation. So it is enough to take absolute values of these and then make regression model in which dependent variable would be absolute values of residuals, and independence will be the set of predictors from original model. So first of all, I would need to compute new column, which will be only absolute values of these residuals, and then apply regression computation. So if I would like to compute absolute value, the easiest step would be go into transform, computing variable. I would only assign some new name. So I would take ABS as absolute values of residual RES, and computation would be based on functions. So I would take, for example, all functions, or if you like, you can take only arithmetic. And the first one is function called ABS. I guess that in Jamovi it was the same function. So absolute value is called usually ABS. I would take this function up. So ABS. And question tag is saying, okay, for which variable you would like to compute absolute value? And this is unstandardized residual, the last one variable in my data matrix. So I would move it to the right window. So currently I'm computing absolute values of residuals. Technical name for this variable is RES_1. So here it is. I can only check briefly whether it works. So it seems that instead of minus, here there is plus, there is plus, there is still plus. So this is absolute value of previous column. And once again, for computation of heteroskedasticity by Glejser's test, it is enough to go into regression linear. And instead of price as dependent, I would take absolute values of residuals. Here it is. And here I would get results, only I still save residuals for this model, so that's useless. But still, here we have the evaluation of heteroskedasticity by Glejser's test. So big T value and small p value means there is heteroskedasticity in my data. So still, maybe I should somehow change computation for my model. And we know theoretically from previous discussion that weighted least square is the technique that can help in the case of heteroskedasticity and also in the case of autocorrelation. So if you would like to perform this weighted least square technique, here in SPSS, you can find also the new window for weighting. So here, if you create some weight, we will not go into details, so you can apply weighted least square techniques here directly by dialog in SPSS. In Jamovi and chess, there is currently no such option for this weighting. So here it is. And last step for SPSS introduction into regression diagnostics would be to find whether there is some multicollinearity. So it means some strong relationship for predictors. So for simplicity, I would take 3 predictors for the frost inside, size, whether the flat is new or not, and the size of the balcony. So these 3 predictors will be included into my regression model. So once again, I will go into linear regression. I will only cancel options for saving residuals. Price would be dependent, size will be frost independent, and new and balcony will be second and the third predictor. And if I would like to find some multicollinearity diagnostics, I guess it is included in statistics here. And here you can, the dialog here on the right side, the lowest one, which is called simply collinearity diagnostics. It will include VIF and also some other statistics here. So there will be new columns in table with coefficients, and there will be also one separate table with condition index, which was not included in Jamovi environment. So we will show how it works in SPSS. So here it is, and here we have 2 new columns, which are called collinearity diagnostics with tolerances and VIFs. So we know about these from previous lecture. Only the difference in Jamovi environment was that these tolerances and VIFs were in separate table. So once again, recommendation for tolerance. If it is below 0.2, or some people say below 0.1, so this is strong multicollinearity and you should solve it. For VIFs, just opposite, above 5 or above 10 is recommendation that you should solve the problem. So that's tolerances and VIFs for every predictor. Here we can see no strange points or no strange values. So there is no multicollinearity in this model at all. And if I go down, this is new table, which is not present in Jamovi as well as in CHESP environments. It is called simply collinearity diagnostics. And for us, the most important result can be found in a column which is called condition index. And we are trying to inquire the last one value, which is 5 here. And from theoretical presentation last time, you know that values approximately above 30 means strong relationship or strong multicollinearity between predictors. Here, as we have approximately 5, there are no doubts that predictors are not correlated strongly, and it's not necessary to solve multicollinearity problem in my data. So that's condition index. Once again, every time I'm interpreting last one value in the column, which is called condition index. And only for technical insight, this condition index is nothing more than the ratio between eigenvalue, which is the first one, and the last one. So if you would take 2.343 divided by 0.092, so you would get this value approximately 5. So if you do not believe SPSS, you can compute it alone. So that's all about regression diagnostic steps in SPSS. So if you would decide to compute your own homework instead of Jamovi in SPSS, feel free. You have all these options available. Okay, so that's all for this first insight into regression diagnostics in SPSS.